Okay, so some background. We're probably all familiar with the idea of automatic speech recognition or speech to text, this idea that you can talk into your phone and then it magically takes the sound and converts it into the words that you're saying. We've been wanting to do this at least since we figured out that you could convert sound into pictures. So that's what I'm showing you some examples of here. These are spectrograms, right? So if you've never seen this, this is what it looks like if you take some sound and then you do some math to make a picture out of it. And sort of the state of the art, again, as probably a lot of us know, for doing this is using neural networks, specifically a long short-term memory network, some descendant of that family of networks. And just to give you a sense of that, so this graph here, which is from this blog post, which is really good about the state of the art of speech recognition. And we'll tweet out the slides later, by the way. So this is word error rate, which is a very commonly used metric in the field. On the y-axis and on the x-axis is time. And you can see, because of the little oval that I made, that all those models at the end use bidirectional LSTMs of one sort or another. So this long short-term memory LSTM, that's what it stands for. That is a recurrent connection in your neural network, which is supposed to capture these dependencies across time, right? And so you might think that if you can capture long and short-term dependencies across time, you would do a better job of being able to go from speech to text because you have all these different levels of dependency across time in speech. Okay. But the state-of-the-art networks that use LSTMs avoid segmentation. What do I mean by segmentation? So here's this waveform. This is from Graves et al. 2005. This is a paper on connectious temporal classification, which again is part of this family of these LSTM networks. That's their name for their architecture in this paper. But what the figure is showing at the top is this waveform from sound. This is three words, the, sound of, and you can see the phonemes divided up by those dashed lines. And you could just have some algorithm, whatever it is, could be like supervised or like a support vector machine, some supervised learning algorithm, and it just classifies every time frame in your sound and says, this is part of phoneme the, or whatever. And when you do that, you get implicit segmentation, right? When one phoneme stops and another one starts in your series of time bins, then you get a segment. But with this connectionist temporal classification and all these other LSTM models, you just map straight from your sound to your words. So you neglect the segmenting of speech. You just go right from sound to text. And that's what I'm showing here with these arrows, right? So you don't have any idea of where one word starts or stops. You just go right from here's my sound to here's my word. And you just pick the peak for whatever probability you're looking at to decide what word is what. But there's a lot of cases where you would care about the segmentation, right? So if you're trying to diagnose a speech disorder, like here's a spectrogram of stuttering, you want to be able to find the links of the different speech segments to try and diagnose how bad that stuttering is. Or if you think about many other speech disorders where we care about something like the pitch of someone's voice, you can't really measure the pitch accurately if you can't find every segment. Likewise, if you're trying to figure out how the brain controls speech, it's hard to relate something like muscle activity or brain activity to speech if you can't figure out where words start or stop. And then last but not least, if you're thinking about these models we have for automatic speech recognition, maybe, we don't know yet, or at least there hasn't been a lot of work done yet to ask whether having some representation of segments would help you do better on recognizing speech with a lot of background noise or with different accents. And again, if you look at that blog post that I linked to at the beginning, it has a lot of some good points about what these models have issues with now. Okay, so stepping back, segmentation writ large is about finding signal in noise, right? So Again, as a lot of us probably know, there's been a ton of work done on object recognition. So can I find a bounding box for some object in my image? Or can I segment the image so that every pixel belongs to one class or another? In terms of time series, right, you can try to find the piano keys when they get played in some piece of music, or find events in background noise like footsteps or explosions. And then last but not least, our favorite is, can you find elements of birdsong in a spectrogram? Okay, so part of the reason we are happy to be giving this talk is we want to propose this idea that we might be able to use birdsong as a sort of an MNIST for benchmarking these segmentation architectures, right? So this is one repository that our lab, Sober Lab, has put up, but a lot of the labs in the songbird field are working together to try to get more of this data out there. And let me tell you a little bit. We'll go into like why we care about birdsong. So we both work in labs where we study them as a way to try to figure out how the brain learns and controls speech and similar motor skills. So songbirds, you might not know, learn their song in a way that's very similar to how we learn speech. So they are taught it by a tutor when they're juveniles, and they acquire it during a sensitive period, just like we learn to talk, from our parents or whoever we grew up around. And you can learn more about the work that all these different labs do if you go to songbirdsscience.com. And so what's kind of nice about birdsong is that you can segment it into what we call syllables. So I've been talking about spectrograms, but not defining what a spectrogram is. So just to make sure we're all on the same page, on the y-axis of that picture on the top in the lovely jet color scheme, is frequency, and on the x-axis is time, right? So that's the spectrogram. And then what I'm showing you on the plot below that is just the amplitude of the bird's song. And the way that we find the segments, typically, is we just look for crossings of the threshold of the amplitude, and that's what those red horizontal lines are. So we would just call those the segments, those are our syllables, and then we just arbitrarily apply some labels to the bird's song. And what's nice about the song of many species is that it's pretty easy to segment into these syllables. You just look for these brief silences that separate the syllables. And this is easier than speech because, in speech our syllables all run together. So, if you want to have this hand-labeled data set, something like time it, however you prefer to pronounce that, right? That someone has to sit there by hand and give their best guess about when one speech syllable starts and another one stops. But song can vary very much greatly between species, as much as phonemes and syntax vary between languages. So here's a zebrafinch song, just 1 second of its song. They have one motif that they'll just sing over and over throughout their adult life. By comparison, here's Bengalese finch song. So they'll have one syllable that we call branch points, a few syllables that will branch to 2 or more syllables, and this gives them a sort of syntax to their song. And then last but not least, canaries, which Yarden is working with. So there's that 1 second of zebrafinch song down at the bottom for comparison. A canary song can last 30 seconds to a minute, and it can have tens of different types of syllables, and they can repeat those syllables for varying number of times, right? So what's interesting about this is by using the song of different species, we can see how well these different models, different neural network architectures, for example, generalize. Okay, why do we care about this? So as an example use case from the Sober Lab, we do these behavioral experiments. So this is a spectrogram again. I'm showing you one syllable of one bird's song. It'll sing this thousands of times a day. We can target this with the computer in real time. Each time it sings slightly different so that there's a distribution of pitches for each syllable. And if we target part of that distribution with the computer, we can play a blast of white noise whenever it sings in that targeted part of the distribution. And when we do that, as I'm showing you in cartoon form here, the pitch rapidly shifts up. So the bird doesn't like this white noise blast, and it can very rapidly adjust to avoid that noise. And so this tells us that the birds can still control their song as adults once they finish learning, which we didn't know about until just a few years ago.
Yeah. Hello. The use case in the Yarden lab has to do with canary songs. So we record canaries. And we not only record their song, which is like the spectrogram up there, but we also record neural signals. And we do that by implanting those mini microscopes on this sketch that you see there. It's basically a camera that can look and see when there is any signal in neurons. And so to analyze this kind of data, song together with neural activity, what we want to do is relate the two. So it matters to be very, very precise and to be able to say exactly which syllable is sung at every given moment and segment them very precisely. I'll show you how this data looks when it's attached to a segmented song and the video that the camera sees. What you'll see, it'll be quite a mess. I mean, but what you'll see is a lot of flashing cells in the video, and in the bottom left side, you'll see the spectrogram, which is already annotated. So you'll see the repeating syllable, and I will highlight the syllable that's currently being sung. There's audio to that. It's not projected. I hope you can hear it. Yeah, it's a bit of a noise blast, I'm sorry. So, but what I can do with it and what we do is relate it to the neural activity and the song. And so just briefly exemplifying that, I can just pick up one of those or two of those flashing cells, and then in the figures here, show you two figures for two cells. And the signal is, all those traces are for multiple repetitions of these songs, all aligned to time 0, which is when the birds start repeating this long syllable. So I just play again. Okay, very simple. And just in this example, you can see the top cell. I mean, the color coded for the traces is just for the different type of syllables. So the black ones are when these long syllables are being sung. And the first cell in the top prefers the first syllable, and the cell at the bottom prefers the other two syllables. And this is the kind of findings we'll look and find recently in the Yarden lab.
Okay, so that's some use cases, like why do we care about being able to segment and classify these syllables? And again, thinking about working with the songbirds, they sing thousands of songs a day, so this is something we need to automate. You might ask, right, well, why can't you just use some off-the-shelf machine learning method, like some algorithm like k-nearest neighbors or support vector machine, and just classify these segments, because you just told me that they're really easy to pick out of the song. And in fact, I've developed a library that does that, hybrid vocal classifier, so you can check that out. The issue is that these methods fail as soon as the segmenting fails. So if you have noise in the background, like those white noise bursts that I showed you, or if you have a change in the song because of the experiment, or if you're working with a species that has a song that's not easily segmented, like the canary song, so they can dramatically change the volume of their song. They're like vocal gymnastics. So the automated segmentation that we normally do fails when trying to work with their song. So we need something that does the segmentation for us, some newer method. And of course, like the answer to everything else, it's neural networks. But then the question is, which neural network? So we have some very preliminary results to show you to try to get at this question. We're comparing neural network architectures. And what we need them to be able to do, the output should find the edges of the syllables. So in other words, they should segment. And then they should label the syllables. So we want to get out a classification, just like the speech-to-text networks do. And as our training data, we're just taking these spectrograms and showing it to the network. And then as an output, we're getting, for every time bin, some label, right? So we get our implicit segmentation that way, like I talked about before. And so one way you might think to do this, one architecture, is a fully convolutional network. And so, we don't have time to go into the details in this. I'm happy to talk with people offline, and I'm sure Yarden is too. But just as a very high level, fully convolutional network, the input again is a spectrogram. the way that these convolutions work, as many of us have probably seen before, is you have this layer made up of filters or kernels that do the convolution. Each kernel contains a weight, and the weights are adjusted as the algorithm trains the network. And hopefully it learns to represent some feature. So you might think of some feature in the syllable that it would learn to recognize. And then you have some layer that hopefully reduces the number of parameters, like a max pooling layer that takes the max values across your kernel. And then hopefully you have this reduced representation that's capturing whatever is essential about the syllables. And you might spit out some classification, like is that syllable A or syllable B or syllable C. But what has been more recently done is to instead return an output that's the same size as the input. So this is a fully convolutional network, and so now every point in your output is a classification. And so you can do this with your spectrogram as well, and then you can use some simple method like sum down the columns of your spectrogram and just take the majority vote, and that would give you this segmentation. And so this is just a picture of what that would look like with spectrograms from this Komura Okanoya paper, just to give you some idea. Just think they use like this sliding window that moves across instead of being fully convolutional, but the output is the same. And there's links to this actual paper in the code at the end.
Yeah, a different approach is, or an additional approach is to remember that the spectrograms are not just like images. The axes mean different things. So one is time, and the other is frequency. So frequency is pretty much like a spatial axis of the image, and indeed different syllables differ in their frequency features, and using the same convolutional networks, we can maybe train filters to find those features. But time, especially in songbirds or speech or a lot of time series data sets, has structure. So we have long and short term, and I'm hinting to the rest of it, right? Correlations in the data itself. So what we do is indeed train those convolutional networks to pick up those localized spectral-temporal features, but then we feed this into a recurrent network, an LSTM or bidirectional LSTM, that hopefully or potentially can capture those long and short duration correlations. The output of this layer can then be projected on the different labels for every time bin.
And so the way that we're going to compare these architectures is we're going to make a learning curve. So this isn't a learning curve, and that's why it's in quotes, like you would normally use to check that your model is actually learning. What we care about here is which model does the best given the least amount of training data. So for experimentalists, we want to label the least amount of songs and get the best accuracy. And then the way we're going to look at that is a standard approach where you're going to take your training data and repeat it several times. So for each replicate, we have this training data set, and we're going to then look on a separate test set and see what the accuracy is. And so just grab, say we're training it with 15 seconds of training data, grab from our bigger training data set 5 times, some number of songs that adds up to 15 seconds, and then take the average across that number of songs. And the accuracy that we're looking at will be frame-wise accuracy. So you could think of other metrics, something like a word error rate. You could have the syllable error rate for a songbird. But for now, we just want to look at how well does it classify every frame. And if it's doing pretty well at that level, then we might think that it's also going to be doing well if we look at something like the syllable error rate. So here's the initial results. And I think what you'll notice is that there's no clear difference so far. So if anything, the CNN by LSTM is doing a little better than the FCN. So this is using, as best as I could, the same hyperparameters for each network. Right, so you're seeing the training set size is on the x-axis and the accuracy is on the y-axis. And just looking at the average, the error rate is lower for the CNN by LSTM.
But we can also ask how do the hyperparameters matter in this question. And in developing this algorithm, I could take more frequency bins or get better frequency resolution to capture more features of the canary than other birds' spectrograms. And that also forces me to use more hidden layers, hidden units in the LSTM. And then I can, in this just example, I trained the network with 30 training files of Bengalese finch songs. This amounts to about 400 seconds of data. But then I held out the grand majority of files, so about 900 files to create test set distribution. And what I'm showing you here on the y-axis for every file is the fraction of error in frame-wise or bin-wise. And this is the distribution for the entire test set, and the median is about 1.4% per file. And you can ask, okay, is this specific to this bird or to this bird species? Well, the simplest case is to go back to the zebra finches that just keeps singing the same motif again and again and again. So a bit of a strawman argument. But again, the distribution here is only on the held out data, training the network on about 14 files and testing on about 10 times that. And the median here is below, median of error bins, fraction of error bins per file is less than 1%.
Okay, so I think that, again, these are very initial results, and I think we're probably not the first people to face this question of, does it matter if you have a recurrent connection in your directed acyclic graph, or sorry, neural network, right? So especially in this case where you have the whole sound, right? You finish speaking, and now you're trying to segment it. Does it matter if your network is recurrent? So this is a bigger question, and I think, as we showed, if you use a bunch of if you increase the number of parameters as you adjust the hyperparameters, then you can get lower error rate. So we're still working at this. We're doing all our coding in the open, so you can go check it out. Some other questions are, slight changes in the architecture, like this sliding window idea that we told you about. Maybe if you just have a big kernel that slides along the whole spectrogram, you can get the segmentation out that way. And we hope, again, to apply this not just to the work that we're doing in our lab to segment song, but that this might be useful for people looking at things like speech disorders or brain control of speech and automatic speech recognition possibly as well. So we'd like to thank our labs, Gardner and Sober Lab, and our funding sources, NIH, NSF. We both benefited from the NVIDIA's GPU grant, which made it possible for us to train a bunch of these models. And we will tweet out the slides, so you can go check out our code on GitHub. We're happy to get feedback from people. I also want to thank Yarden. This has been a really great collaboration, and he's really pushed me in all the ways that I needed. So, and of course, thanks to PyData New York City for inviting us.
Thank you, guys.
Hey, you have a question? Sure. Yeah. So the question is, are we trying to classify which bird is singing a song? So no, in this case, we do know which bird species we're working with. So when we train the algorithms, we're just trying to figure out which syllable is being sung from which specific bird. So it's a good question, which we very frequently get, right? So, but this isn't about identifying species. This is like, is this Bengalese finch number 1 syllable A, right? And again, going back to this question of generalization, what you can look at, I think, working with birdsong is, does your model generalize across individual 1, 2, 3, 4, 5, and does it do so as well as some other model? Yeah. Mm-hmm. Sure, yeah. So most of what we use in the lab is homespun, but when it comes to the analysis, we're definitely using the NumPy, SciPy, Matplotlib, Keras.
TensorFlow for development.
We're sort of in the process of putting stuff out?
A lot of it is in the individual labs. So David is, I think, leading a Herculean effort to join all the Songbird labs and create a joint source. But every lab has their own GitHub. The Gardner lab has their own GitHub, and a lot of the data massaging analysis and also capturing homemade code that we have is just out there.
Yeah, so we're working on that, but yeah. Other questions? All right, thanks everybody for
Thank you so much.
listening.